wrap up this commutation issue because we will need it anyway for the next chapter. So might as well talk about it here. So we explained it briefly before, and I will go over the explanation just quickly here. So the idea is the following, right? In this freewheeling diode-based circuit, we added an inductor at the input. What does this inductor do? Typically, we said inductors limit the rate of change of current, right? That's what they typically do. So, which means that the current that is going into this diode will not rise as fast and will not fall as fast, right? That's what it means, right? So, when this diode is turning on, current will rise slower than we would have expected it to rise, right? So, and it will fall slower than we would have expected it to fall as well. So, if this diode was turning on, theoretically speaking, we would be drawing, ideally, current would rise right away, right? That's what we were drawing before, right? And same thing with when this is rising, when this diode is turning on, it means it picked up all the current from the freewheeling diode, right? In the positive half cycle, remember, without this inductor, in the positive half cycle, D1 was on. As soon as we get into the negative half cycle, D2 was turning on, right? And it was picking up all the current, right? So, which means that if this is turning on, the diode 2 was turning off. So it was on here and then turning off right here, right? So this was the case for when there was no source inductance. In the presence of a source inductance, again, what we said inductors do is delay the change in current. So current will not rise as fast anymore. Current will slowly rise. And current will slowly fall. Right? So in the previous case, both diodes are never on at the same time, in the red case. In the blue case, there's obviously an area here where both devices are conducting current. Both devices are conducting current means both devices are on. If both devices are on, then this is a short circuit and this is a short circuit. Okay? If both of them are short circuits, what does the current out of this supply look like? It's the voltage of this source across this inductor, right? I mean, I have a voltage source and an inductor. That's it. That's all I have. So the voltage across the inductor is equal to the supply voltage, right? That's what we have here. And then, so this is the voltage across the inductor. From L is equal to L di by dt, I can calculate the current through the inductor by the integration, right? Calculate the current through the inductor by the integration. So I would calculate ID1, which is equal to IS, by the integration of the voltage equation, right? How do I calculate ID2? ID2 is equal to the inductor current, the output inductor current, which we said we will assume constant. We said that we will assume this inductor is pretty large, so the current here will be a constant value, IL. So, which means that if this is IL and this is ID1, then ID2 is the difference between these two currents, right? According to Kirchhoff's current law. So this is ID2 is equal to IL minus IS. What is IS equal to? IS is equal to the integration of the voltage equation. So Vmax sine omega t, you integrate it, you get the Vmax over omega L, 1 minus cosine omega t. So that's the integration of the voltage equation. So this is ID2 current, and this is this is IS portion of it, and this is IL, which is the constant value that we said is, assuming a large inductor in the output here. So this is ID2. So now I have an equation for ID2 current. This ID2 current, what happens to it? This is ID1. ID2 current starts high, and then the device will turn off. So the current will go to 0. But we said that now it will go to 0 after a period of time. This period of time here, we will say that ID2 at time u is equal to 0. Right? So I would like to find out, this is something I know, that the current will fall at the point u. What is this point u? So we're trying to find that point u. So ID2 of 0, so ID2 of u is equal to 0. So we'll equate this, substitute, instead of t, it will be, instead of omega t, we'll put u. Right? So instead of an omega t, we'll put the angle u that we have. So ID2 of u is equal to 0. So we do that. We create this equality and solve for u, right? That the only thing will be missing here is u, right? So instead of omega t, I put my u here, and then I will have an equation in terms of IL, in terms of Vmax, in terms of inductance, in terms of IL, omega, and Vmax, and my inductance. Okay, so I solve this equation for u, and then this u, now I can use to find out how much loss I had in my output voltage. Without the commutation, I had no zero here. With the commutation, because both diodes are on at the same time, right, we ended up with a voltage at the output equal to zero. Right, so we lost a little bit of the output voltage. How much of the output voltage? We will integrate. Instead of integrating the Vmax sine omega t from 0 to pi, right, or 0 to 2 pi, and then here it's 0, we will integrate from u to pi. Right? So that is the effect of commutation.
So why would you do this?
Because all power systems are modeled as a synchronous generator, and synchronous generators are modeled like this: a source with an inductor in series, and then you put your load, right? Whatever load you have here. So anytime you have a AC source, you will always be modeling it as an ideal voltage source with a reactance in series in a power system. So there's always this effect of source inductance here. So it's a big thing in power systems, source inductance, because in power systems, we are concerned about, okay, if a short circuit happens here, what happens? Then you have to find out the impedance from this point all the way to the generator. And this impedance in power systems is always modeled as reactances. Why? Because typically in a power system, you are using cables with a low loss. Otherwise, you're spending all your generator power as power losses, right? So you typically select large cables with low resistance. That's why these transmission lines, they don't even have a jacket on top of them, right? They're just insulated. They're conductors. They're conducting materials that just have a large area so that they can reduce the resistance here. So what is the effective model? It's theoretically there's some small resistance, but typically we neglect that in power systems and we just consider the reactance here. So that's why source inductance is important, because as a power engineer, you are going to connect your big drives in RasGas or Qatargas or whatever to the utility. The utility, how do you model that? You model that as a voltage source and an inductor in series. And that's how you would calculate the fault level at your utility. You will calculate the fault level at your utility that way. You will be given by Kahrama. They will tell you the equivalent impedance is so-and-so, equivalent series impedance until your bus, your input terminals, is so-and-so. So you put that impedance, and then you put a short circuit there and see how much current will flow. And for 59, we do a lot of these calculations. So it's always there. That's why we have to consider it. Yeah. And of course, this is a simple circuit. Okay, can you imagine in a three-phase circuit with SCRs how complicated the commutation issue gets? I mean, it's an issue, for example, that one of the industries here at some point was having serious issues because of commutation and the effect of the source inductance. Yeah. And, the drives were turning off and they were getting weird control signals and stuff like that. So it's something to consider. So anyway, so we understand that it has an effect. It will change the voltage that you're expecting, right? So if you're controlling something and you're expecting a certain voltage, you should consider commutation because that will affect the value of voltage that you will see on your output. Yeah. Okay, so this wraps up chapter 3. So chapter 4.
So we consider commutation a loss.
It's a power quality issue. I think it's not a loss because it's a. I mean, it's a. No, I mean it's the current is circulating in the circuit, so it's an extra loss in your power converter, but not your load. So yeah, you can consider it as a loss, but for me, it's more of a power quality issue. Like it's a power quality and a control issue. It affects control of large converters with power electronics. Yes, ma'am.
This is the last chapter on the exam?
Depends on when we have the exam. Right?
If
we will cover until maybe like a few days, 3, 4, 5 days before the exam. So hopefully this is the last chapter.
Okay.
Let's hopefully that's the last chapter. Huh? Ask lots of questions. Yeah.
Yeah.
Okay, the next chapter, full wave rectifiers. You will see that this chapter, it will be very difficult to ask lots of questions because we will see very similar output voltages and currents. So if we understood them before, we will not have lots of questions to ask. But we're just complicating the circuits a little bit, and we will see some advantages of full wave rectifiers. You've studied, this briefly in 325. I'm sure you've seen some of these circuits. You just didn't go into the deeper analysis and of the output voltages and output currents and input currents, etc., etc. So this is what you've probably seen before in 325. This is equivalent to this. We just like to draw it differently in power electronics. In power electronics, people like to draw this differently. And so even though this looks more like a bridge, Wheatstone bridge that you've studied before, and we actually call it the bridge rectifier, full bridge or bridge rectifier converter, but we still like to draw it this way. Okay, so it's easier to understand and explain when you draw it this way, actually. So, what's happening? What's happening here? Again, positive half cycle. Positive half cycle. This is the most positive terminal in your circuit. This is the most negative terminal in your circuit. Correct? So if this is the most positive terminal, then this is definitely less positive. If this is the most negative terminal in your circuit, then this is definitely more positive, right? So then this diode has a good, again, and you have a circuit connected here. So if you have a circuit connected that will allow current to flow, and certain diodes have favorable conditions to conduct. Let's see which ones have favorable conditions to conduct. If the voltage here is more positive than here, this has a favorable condition to conduct. How about this diode? This diode, this is the most negative potential in the circuit. Then this is definitely more positive, right? Then this diode will not conduct in the positive half cycle, right? Do we agree? Another reason it won't conduct is that as soon as this diode turns on and starts to conduct, the most positive potential here will be transferred to the top here as well, and it will block this diode from conducting, right? So the two top diodes, they cannot conduct at the same time. If one conducts, it will block the other from conducting. Same thing with the bottom diode. This is the most negative potential in the circuit. This is the most positive potential. If this is the most positive potential in the circuit, then this is definitely more negative. So this diode will not conduct unless there is no other path for the current to flow, and then there is energy stored in the circuit that is pushing current to the circuit, right? But now I have a resistive load, so I don't have to worry about that. So now this diode will not conduct, and this diode will not conduct. How about this diode? This is the most negative potential in the circuit. This is definitely more positive potential, so this diode can conduct. Now, do I have a path for the current to flow? I have a path for the current to flow from here, through this diode, through this load, and back through this diode to my supply. So I have a closed path for the current to flow. So current, voltage across the resistor will cause current to flow. This current has diode D1 and diode D2 to flow through. We're happy. The load is happy. You're okay? Okay. So we're fine. So what does now the circuit look like? What's the equivalent circuit of this converter when diodes D1 and D2 are conducting? A voltage source and a resistor, right? That's it. So what does the output voltage look like when D1 and D2 are conducting? Same as the input voltage, exactly, right? So it's exactly the same as the input voltage. So the output voltage will look the same as the input voltage for my positive half cycle. How about for the negative half cycle? Negative half cycle, we flip the terminals here. So this is the most positive terminal in the circuit. This is the most negative terminal in the circuit. Now let me erase this blue stuff. This is the most positive potential. This is the most negative potential. Most positive here, most negative here. right? So this is the most negative, this is definitely more positive, right? So this does not conduct, right? This is the most positive, then this is more negative. This will not conduct. This is the most positive potential in the circuit. Definitely here will be something less positive. So this can conduct. How about here? This is the most negative potential in the circuit. Here, definitely this would be more positive. So this can conduct. So now in the negative half cycle, as soon as I have the negative half cycle, I have a path for the current to flow, right? Even if I have an RL circuit, the circuit will behave the same way because the diodes D3 and D4 would be allowed to favorably conduct in the negative half cycle. So as soon as I have a negative half cycle, diodes D3 and D4 will start conducting. Even if I have an RL load, if I have an RL load with a source, same. Right? So now the output voltage, what does the equivalent circuit now look like? Same, but with a flipped polarity of the voltage, right? I flip the polarity of my voltage source. So basically, I have an output voltage that looks like this. It's equal to negative of the input voltage, negative of the source voltage. The original polarity, right? The original polarity of the voltage, I was measuring here negative, but now I flipped the polarity, right? You flipped your positive and negative, so that's why I can draw this on the top here. Okay? How about, so this is output voltage. How about the currents? How about the output current? How about the output current? Exactly. It's always the output voltage divided by the value of the resistance. So it looks exactly the same. Right? Exactly the same. This is the output current. And note here, this is the way we draw it, the way the power electronics people draw the bridges is more self-explanatory, in my personal opinion. Because look at the diodes; they're both pointing up. What does this tell you? Current can only flow out this way. It tells you the output is DC. You cannot have current going back. Current will never come back into the circuit, into these diodes, right? As soon as you try to push current back, the diodes disconnect, right? So versus here, it's more difficult to see that, in my opinion. Anyway, actually, it's different for you. It's easy to see that the current is always, out of these diodes, never comes back from the load when you draw it this way. But on one exam, I think I just changed the way I drew it. Actually, I think I drew 2 half bridges, like from the previous chapter. I think I drew 2 half bridges in parallel. Like I just drew it in a different way. And when I drew 2 half bridges in parallel in a different way to create a full bridge, then people got confused. Right? So I think maybe that's the exam that I have on the website. I'm not sure. I'll check it. But it was nothing but 2 half bridges in parallel, operating in parallel, to create a full bridge at the end. Yes, sir.
Half bridges in parallel will be two diodes pointing at each other, right?
No, but I drew it differently because I had a transformer in there as well because we will study a transformer circuit right now. Yeah. So okay, so this was the output current. Anything else? No, this circuit. That's it. So what's the benefit of this circuit versus the half-wave rectifier? Obviously, I get more average output voltage, right? Because before I was getting 1 half cycle only. Now I get 2. I still have huge ripple, right? Right, my ripple is very high, so we'll still obviously look at having a capacitor here as well to limit the ripple. But the capacitor here will need to be a lot smaller because what did we do here to the voltage that the capacitor is trying to filter? Double its frequency. Remember we had an equation where the voltage ripple is equal to the inverse is inversely proportional to frequency, inversely proportional to size of the capacitor. Here I've doubled the frequency, which means my capacitance can be half the size. Right, so that's one thing we will see later, but the analysis will be exactly the same. That's why this chapter is exactly like before, just very few minor changes here.
So, but we also need an inductor for the current.
Inductor for the current, where?
Because
We will add RL because of what?
I mean, you have a capacitor there.
I will look at we will add that here because we didn't talk about that in the half wave rectifier. But in this chapter we add the capacitor in addition to of capacitor. We add the inductor in addition to the capacitor. We will do that, and I briefly said that the effect is these big pulses on the capacitor current, they will be sort of smoothed out, and we will see that in this chapter. Yeah. Okay, here. What else do we need to discuss? Here we need to discuss the rating, the voltage rating of these diodes, right? When this diode is off, what voltage do you see across it? So if this is off, it means this is on, right? And then this means this is also off, and it means this is on. It sees what? So this is this diode voltage. And if I go around, let's say I go around the loop here. So I see this diode voltage, and I see 0, and I see, let's go around this loop. This is a loop, right? This is a closed loop. An easy closed loop to go around, right? So this is current coming out of here, going, it was, this is so the current's coming out of here, going through D3, right, going back to the output and coming back through D4, right? This is my closed loop here, right? Here, yes. Let me draw that in blue. Let me erase this. Okay. In the negative half cycle, so current is coming out of my source through this diode. So this is a short circuit, right? Current goes to my load and back through D4, right? That's the path of current flow. So this diode is now an open circuit. So I need to know what is the voltage rating of this diode. So how do I find that? I go around the loop. So this is the same voltage here, right? This is just one node. So the voltage here, this is a short circuit, right? If I go around the loop, if I go around this loop, here, I see the source, and then I go back to my diode. So obviously the voltage rating of this diode will be equal to Vs, right? But is it the same polarity or opposite polarity? Look at the positive here. Our positive notation for Vd is connected to the negative terminal of the Vs. So it's just the opposite polarity of the source. So you'd expect that the diode voltage you would draw in the negative half cycle. Positive half cycle, this diode is on, right? If I ask you to draw Vd1, in the positive half cycle, this diode is on, so its voltage is 0. In the negative half cycle, the voltage is equal to the supply voltage. Okay? So let's see here the waveforms that I drew. So this is our input voltage. We said we went through the output voltage. And Vd1, we said that Vd1 and Vd2, diode 1 and diode 2, they conduct in the positive half cycles. So in the negative half cycles, they carry the supply voltage. Okay? Yes? No? What is the diode rating? Here. It is the max voltage of the supply. That's what we're trying to see. Why? Because in another circuit also that creates an output voltage at a full wave rectified waveform, the diode voltage will be different. It will not be the full voltage. It will be double the voltage double the supply voltage, yeah. And we'll see why. How about diode 3 and diode 4? Again, they just alternate, right? If diode 3 and diode 4, they're on in the second half cycle, and in the first half cycle they see the supply voltage. Okay? Yes? No? Output current, we drew ID1 and ID2. We said that the current looks exactly, the output current looks exactly like the output voltage, right? And part of the output current will be carried by diode 1 and 2, and then the other part will be carried by diode 3 and 4, right? So when we're in the positive half cycle, current is carried by diode 1 and diode 2. So if I draw diode 1 and diode 2 current, it is this part of the output current. And then diode 3 and diode 4 carry current in the second half cycle. And note that they are both in the same direction. Since diode 3 and diode 4 are all everything's pointing up. All the diodes are pointing up. The current, and if we assume that current is flowing from the cathode to the anode of the diode, then all the diodes have the same polarity of current. Yes?
What does the source current look like?
That's a good question. Yeah. So the answer was there, but we will show you how to derive it. So now we want to derive. Typically, all you're concerned about is the source current. I don't care. I'm the utility. I don't care what happens inside your converter. You do whatever you want. But you're consuming my current. So I need to make sure that you're not polluting my current, causing my power quality to be poor, right? So it's always, you will always be asked to calculate the source current because you want to always calculate your power consumed from the supply, your power factor, etc., etc. That's what you care about typically. So what is your source current equal to? So this is what? Diode 1 current. And this is what? What is this current?
Diode 3.
Diode 4. Why is it 2? This is a node here. This is a node. Coming into this node, coming out of the node is diode 1 current. Coming into the node is diode 4 current. And coming into the node from here is the supply current. So this is, so whatever's coming in, I is IS plus ID4 is equal to ID1. So if I want to calculate IS is equal to ID1 minus ID4. So ID1 is here, right? ID4 is here. So 0 minus something positive is a negative number, but the same shape. So what does the supply current look like? It's a sine wave. So in the second half cycle, it's a sine. I mean, you just flip the diode 4 current, and your input source current in this case is a sine wave. So what is the power factor of this converter? Unity power factor, right? You have a nice sine wave that's in phase with the voltage. Yes, sir.
So how do you use the source? Can you give us an example?
How do I what?
Produce the
Next converter will do that. If you're gonna draw something non-sinusoidal, then you're gonna have harmonics. Yeah. So that's what the next, not the next one, the following one after it. Yeah, we will do that. So that's the full bridge rectifier. Again, we said that the advantage was doubling the average voltage. Really. Yeah. So this is called a center tapped transformer rectifier, also full wave. So we will see that the output voltage will be a full wave rectified waveform, and we will see why shortly. What is the difference though between our half wave rectifier and our full wave rectifier from a supply current perspective? Remember the half wave rectifier? What was the current shape in the half wave rectifier? There was no negative, right? So it had an average value, so I cannot, and we said we cannot push it through a transformer. So this is a big drawback in half wave rectifier. So even though it's a simple circuit to create DC, it is not very useful at all, because typically you want to, take this 240 volts, for example, and convert it to 9, 10, whatever you want to power up your electronics here. And you need to step that down. So how do you step that down? You cannot use a half-wave rectifier in that case, easily. If you use a half-wave rectifier, then you cannot use a transformer. Transformers are a very nice, easy way to step down voltages and bring them down to a safe working condition. Right? So here I can use a transformer, right? And that's where this next circuit, this is one application of adding a transformer to your circuit. One way of doing it. The other way, of course, is to use a full bridge. So you can add in the previous circuit that we studied. So we can add, we can have your source here, and then you can have, this is your rectifier, diode rectifier. And you can add your transformer here. right? And this will be your transformer. And then you have a nice system where you're stepping down your voltage with a ratio of n from V to V over n over here, and then you can convert that to DC and then put your capacitor here to reduce ripples, right? This is a very common circuit in electronics to utilize. Yeah. So this is nice. You can do that with the previous circuit. Another way to do this is this center tap transformer circuit. The advantage is here I only use 2 diodes. So how does this circuit work? Think of this as 2 sources here. I mean, a source. I mean, it's the same source, but you sort of drew it twice, right? This is VS and this is VS. They're exactly equal, exactly the same. So how does this? How does this circuit work? So in the positive half cycle, what's going to happen? So this is my input voltage as well, same as we had before. And then in my positive half cycle, again, this is the most positive value of the voltage here, the most negative value of between these 2 terminals. How about here? This is the most positive potential between these 2 terminals, and this is the most negative potential between these 2 terminals, right? This is like stacking 2 batteries on top of each other, right? So what will this diode see? So in the positive half cycle, this is a positive potential, then this will be less positive, so negative with respect to it. How about here? This is the most negative potential that this diode is seeing, then this is definitely a little more positive, right? So in the positive half cycle, which diode will conduct? Top diode conducts, the bottom diode is an open circuit. So top diode conducts, bottom diode is an open circuit. So if the top diode conducts, bottom was an open circuit, what is the voltage across the diode?
Minus V0 minus VS2.
So here I have VS, right? And then since this diode is conducting, and I have VS here as well, they're both equal to each other, right? Assuming they're both equal to each other. If this is VS, this is VS, this is a short circuit, then where is this VS applied? This voltage is equal to this voltage, right? Current's flowing this way, then this voltage is equal to this voltage. So what is the diode voltage equal to?
Minus 2 V0.
It's equal to, so all 3, so VD plus VS plus VS is equal to 0, right? So VD is equal to minus 2 VS, right? You add, these 3 are all in the same direction, right? These 3 arrows, they're in the same direction. So you add them up equal to 0, so you solve for VD is equal to minus 2 VS. Yes? No? So it's twice the supply voltage, right? It's twice the supply voltage. So the diode 2 in the positive half cycle here. This is VD2. VD2, the supply voltage was positive, right? I'm seeing minus 2 times VS, minus 2 times VS across VD2. So it's a negative, it's an opposite polarity of the supply voltage, and it's twice its peak value. Okay? Yes, sir.
VS1 and 2 are half of the VS on the other side.
Yeah, I mean it's.
Unity.
So I should have drawn it as I should have said VS prime or VS prime. If I have this, yes. If this is VS, and this is a 1 to 1 to 1 transformer, then what I'm saying is right. Right? Like because if this is a then what I'm saying is that this is a 1 to 2 transformer. Right? This is a 1 to 1 to 1. This number of windings here is equal to number of windings here. Both of them added together is equal to the number of windings on the primary. Right?
And so you get the peak is half the size.
The peak is half? No. The output voltage is equal. No. If this is 1 to 1, then the output voltage on the resistor is equal to the input voltage by the supply as well. So my output voltage is equal to my input voltage. in the positive half cycle, exactly equal. Because I chose 1 to 1 to 1, but I can choose 1 to half to half. In that case, yes, what you're saying is right. The output voltage would be half the value of the peak. Negative half cycle. We just flip everything around, right? These power supplies are flipped. Instead of positive on top, negative on the bottom, we just flip everything. If you flip everything, which diode will conduct? 2 will conduct, 1 will be open circuit. What voltage will it see across it? -2 times Vmax. Same thing. -2 times the supply voltage. To be twice the supply voltage but negative. Right? That's VD1. And the output voltage will still be, since diode 2 is conducting and diode 1 is open, it's an open circuit in the negative half cycle, then this winding's voltage is placed across the resistor. Right? So the output voltage is equal to the supply voltage across the winding 2 here. In the case of 1 to 1 to 1, then it's also equal to the input voltage. Okay? So that's why you get the same full wave rectified waveform that we had in the bridge rectifier. The advantage is I used 2 diodes instead of 4, but the diodes here are rated at twice the voltage, 2 times the voltage, right, than the previous diodes. So it's up to you which way to go. It depends on your loss calculations, right? If your objective is to minimize electronics, right, then you go for 2 diodes, and you don't care about the losses, for example. Then you go for this configuration and not the other configuration. If you care about losses, then you have to calculate the losses. I mean, is your comparison point cost? Do the 4 diodes cost more when they are low voltage, or 2 diodes that are high voltage? I don't know. You have to go and select diodes based on specific voltage and current ratings and compare the manufacturer's data sheets, and they will give you cost.
So it's not necessarily worse. That's too.
Not necessarily worse, not necessarily better. I mean, this is a circuit and that's a circuit. I mean, you have to, maybe at certain ratings, this will be better than the other circuit. Maybe other ratings, the other circuit will be better than this circuit. Because, by the way, here you have to add this center tap in the transformer. The center tap is a cost. Instead of just having a transformer winding simply like that, I have a transformer winding in the middle of the winding. So it's extra work, right? Trying to find where the middle of the winding is, and then you tap that, remove the insulation there, and then you bring a wire out, right? So the cost of the transformer here versus the cost of the transformer there. Just something you have to. I mean, it's a practical thing. Right? Yes.
Can you say again how we got VD plus VS to be 0? And why aren't we including the output in that equation?
I just said that Vs is equal to the output. So here, when this diode is conducting, the voltage here is equal to the voltage here, right? Right. This is a loop. There's nothing else in the loop besides this winding and this resistor. So these 2 voltages are equal to each other, right? So I just call this Vs because it's equal to Vs, the supply voltage. Okay, and then here, same thing. I have, this is my supply voltage, and then this is an open circuit. And I would like to find the voltage here. So I go around a loop. This is my loop here. I add the voltages that are in the same polarity, right? And then the sum of the voltages around the loop is equal to 0. So this voltage was Vd, this voltage was Vs, and then this is V output, but it's also equal to Vs here. So I just put Vs instead. Okay. Same thing so again, since my output voltage is my full wave rectified waveform, then what does my output current look like? Same. I just have my resistor here. The output voltage is always across the resistor, so my output current also looks like the full wave rectified waveform. Now, in my positive half cycle, diode 1 is conducting. So this output current is carried by diode 1 in the positive half cycle. So this is diode 1, ID1, and this is ID2. The current is carried by diode 2 in the negative half cycle. Right? So this is diode 1, diode 2 currents. How about the supply currents? Also sinusoidal. Right? It's also the sine wave because again it's in the positive half cycle this is conducting, negative half cycle this is conducting, this source, this other supply is conducting, and we flipped the source. So in the positive half cycle, it's like, again, since I flipped these sources here when I derived the negative half cycle, then it's like I have to flip the input source symbolically, right? So you will see that the current will also be sinusoidal in this case. So any questions on this circuit? Yes,
When we compare this with the full bridge rectifier,
sure.
the only difference, okay, so the output voltage is still going to be the same,
Yeah,
but the voltage ratings of the diodes will differ.
yeah. Here the voltage rating of the diode is twice the voltage. The voltage diode is rated at twice the value. So the losses, the switching losses. Remember, when I switch, when the diode switches from on to off, what happens? Or when it was on, the voltage was 0, and then the voltage rises when it's off. It's blocking the voltage. So this is V. And then I, when it's on, there is current, and then when it's off, current becomes 0. So if you have twice the voltage, then you have more switching losses. So the losses will be high for switching. Your switching losses will be higher for higher voltages. Because your power loss is what? Equal V times I. So here I have I don't have V. But here I have V and I together. So I have power loss. Yes?
Can you double the diodes in series to reduce the voltage rating of the diode?
Yeah, you can put two diodes like this. Theoretically speaking, yes, but when you put devices in series, power electronic devices in series, you typically have to add balancing circuits. For example, you put two resistors here of the same value. And that will take care of static balancing. Dynamically, during turn on and turn off, these resistors are useless. So we have to use more complicated circuits that perform dynamic balancing across devices. So, I mean, series power device configuration is something that it's a big effort here. So it's there industrially. It's there. Industrially, people use it, and it's an area where companies have an edge over others because of the way they do it. And there are ways to do it, with lossy circuits around it, circuits that have resistors, and there are ways to do it with circuits around the device that don't have resistors. It's ways to do it with circuits around the device that have have a diode in the circuit as well. So it's a big area of study. There's a whole chapter, I think, in the textbook called snubbers, or a few sections, snubber circuits, or snubber circuits. Yeah. So these are circuits that you put around devices to control the turn on and turn off. In general, that's what they do. You want to, because there's a section, for example, in the textbook. We will not cover that. Ideally, you would like to do what? You would like that if you want to, this is current falling down, and this is voltage going up. This is V and this is I. There are some circuits that would do what? They would actually, even though you've tried to turn on the device, they would delay the rise time in voltage until here. So current is falling down. You've given the device a signal to turn on, but this circuit has delayed the rise in voltage. So it will have some capacitor somewhere to change the rate of voltage rise. And what did this do? What did this cause? It caused that now I have this waveform and this waveform. Now I never have a period where I have voltage and current together. Here I have current, 0 voltage, 0 voltage, 0 voltage, 0 voltage, all the way until here. So switching losses are reduced this way. So I'm able to delay voltage. And there are some current circuits that instead of working on the voltage, they work on the current. So they keep the voltage as it is and try to, bring down the current waveform before the voltage waveform rises. Right? So their objective is the same. The objective is to eliminate switching losses. And there's a whole family of converters called zero voltage switching converters and zero current switching converters. So some of them bring the voltage, keep the voltage down to 0, and some of them keep the current at 0 while the voltage rises. You either do this or that. And we will not cover those. I mean, that's a family of converters, that a special case of converters, and their objective is to reduce losses further and further. Right? We will cover the main types of converter topologies. And you can do this zero voltage switching, zero current switching on all type of converters, not only DC to DC converters. You can do it on DC to DC converters, DC to AC converters, AC to DC converters. So on all families of converters that we will study, we study the general case where we don't study like the zero voltage switching case. In all our cases we will consider the voltage following, current rising, and we always have power losses.
Is that about the devices or configuration?
No, it's converters. It's configurations. Not a specific device. The power device is the same MOSFET. But I will put stuff around the MOSFET, and I will maybe change the control of the MOSFET a little bit so that I'm able to do that. Right? So, special cases. You're doing that for senior project? Or?
No, we have an inverter.
Yeah, there you can if you Google search, you find lots of IEEE papers about zero voltage switching inverters, zero voltage switching buck DC-DC converters. They apply. I mean, people take a concept and they apply it on all different types of converters, and people publish papers, and academics are happy, and you get promoted and all of that good stuff, right? Anyway. And then come along these, the very low loss type devices that people don't care to use this stuff anymore because the devices are already, the losses in these devices are already very low. So I don't care to really do zero volt switching or zero current switching because fine, it's complicated, complicates my circuit, increase my cost. I don't care about efficiency anymore because I'm already getting 99.5% efficiency, for example. Right? So, but this is life. Anyway, so we come to your question about what happens to this, how do we distort the supply current? So this is one example of that, and we will go through it now. So now, again, we have our full bridge rectifier. Our full bridge rectifier circuit here. But now I have an RL load, not an R load anymore. So what was happening, again, always when you have an RL load, draw the R case. Okay, draw your R case first. So the R case, the output voltage was this full wave rectified waveform, and the current looked like what? Same as the voltage. Stopped here, right? Now, for the RL case, what happened generally? What did we say? Anytime you have an RL, you draw the R case, and the current will always fall later than the R case, right? Always fall later than the R case. So the resistive case, the current fell here to 0. Where will the inductive case, the current fall? A little bit later. It will start falling a little bit later. So after this pi. Here, coincidentally, what's happening? In the negative half cycle, again, in the positive half cycle, D1 and D2 are conducting, pushing current through my load. The negative half cycle, current wants to flow in the negative half cycle. Okay? Where is it going to go? Is it going to go through D1 and D2 or D3 and D4? Let's think of it. In negative half cycle, what's happening to my supply? And I flip the polarity, right? This is more positive in the negative half cycle, right? It's like flipping the polarity of the battery that you have in the negative half cycle, right? So what's happening here? Then if current is going to go through D2, it's opposing a voltage source. It's opposing a positive voltage. Versus if it goes to D3, it's being aided to flow through the circuit. So as soon as the negative half cycle arrives, it will always pass the beacon, what is it called? Beacon, right? When you relay race, right? You always pass the beacon to D3 and D4. So D1 and D2 will hand over. Or in electrical terms, it will commutate. Right? The switches will commutate, and that's where the commutation thing will happen again. So we have the effect of commutation here on this circuit as well. So D1 and D2 were conducting in the positive half cycle, right? Then comes the negative half cycle. If I have a resistive load, fine. And as soon as the current falls to 0, negative half cycle, the diodes D3 and D4 have a more favorable condition. But now with the RL case, we have to think a little bit and make sure we're on the right track. So with the RL case, we see that the same thing is happening, like the freewheeling diode case. As soon as the negative half cycle arrives, the current that's flowing here needs to decide, do I keep D2 and D1 on, or is it easier to make D1, D3, and D4 on? Which is easier? Which will the circuit like to perform, or is it which is easier for the current to flow? D3 and D4 is easier because the supply voltage is helping you, versus in D1 and D2 the supply voltage is not helping you. Right? So D1 and D2 will commutate, and then D3 and D4 will turn on. Right? So the output voltage will look the same, full wave rectified waveform here. So how about the current? Again, as soon as the device, any of the diodes, D1, D2, or D3 and D4, turn on, what does the circuit look like? Source and RL, right? So what does the inductor voltage equal? So this is my source voltage is equal to VR plus VL. So VL is always equal to VS minus VR. And as soon as, if the inductor voltage, again, VL is equal to L di by dt, IL is equal to 1 over L integral of VL dt, if plus my initial condition. Right? So if my inductor voltage is negative, this integration is a negative value. Right? And if my initial condition happens to be positive, what am I going to do? Add a negative value to a positive number. What will that do? Decrease the current. So as soon as the voltage across the inductor becomes negative, the current will start decreasing. So same thing happens like we described before, right? So at some point, so initially this is steady state. So current is rising. Why does current rise? Because Vs minus Vr is positive. This is my supply voltage, right? And this is my, this. Let's say this is your output current is equal to Vr in shape, right? In shape, the output current is equal to the voltage Vr. So here, Vs minus Vr is a positive number, right? Current rises. Since my voltage is a positive, inductor voltage is positive, the current will keep rising. Until when? Until a point when, fine, this is, the voltage across the resistor is a scaled version, the scaled version of the current. So maybe it will look exactly the same, but maybe a bit higher here, right? Scaled version. So at some point here, VR and VS become equal. Then inductor voltage is 0. This integral becomes 0. I only have my initial condition. What happens after that? After that, VR is greater than VS. So my inductor, this integration is negative, right? This integration is negative. Your current will start decreasing, right? Current starts decreasing until when? You've passed now this pi here. Then the voltage starts rising again. Vs starts rising again. After Vs starts rising, this Vs minus V, and Vr is falling, and Vs is rising. At some point here, right, they become 0. VL becomes 0. VL becomes 0, what happens? VL becomes 0, it's because there is no, L is not 0. It means that the di by dt is 0, so the slope of current at that point is 0. So it makes sense for the current to do this at this point here, right? And then what happens? And then Vs becomes higher than Vr. Here, Vs becomes higher than Vr. So this integration becomes positive again. I keep adding and growing my current, right? So current never falls down to 0. Never falls down. In the full wave rectifier, current never falls down to 0. Okay. Yes, ma'am.
What's the initial condition? I mean, why?
Initial condition was here because we always here they're drawing steady state. So initial condition, fine. Inductor current is 0.
Mm-hmm.
But at some point, as soon as it rises, finished. Then you take the steady state. I mean, here we're only drawing steady state conditions.
Okay.
Right. Initial condition in the case of my integration is the value right before this step. For example, here, before it does this, it was my initial condition was here. The voltage was negative, so I went down.
Mm-hmm.
Then I go to the next step. This Vs minus Vr became positive.
Mm-hmm.
So my initial condition is this point. So it's just the time step before. Yeah. So does it make sense? So now what's happening? Let me erase this stuff. And now let's see so this is now my continuous current waveform. Now we said that in the positive half cycle, D1 and D2 were conducting. And then here, D3 and D4 were conducting. Right? So if I want to draw D1 and D2, the current in diode 1 and the current in diode 2, I take the current waveform only until pi. And that's what I have here. So this is the current flowing in diode 1 and diode 2. This is the current flowing in diode 3 and diode 4. Now we do the same exercise. I want my supply current. It's the difference between diode 1 and diode 3 current. Right? So it's ID1 minus ID3. So it will be this, but flipped. Right? So it's ID1 minus ID3. So here ID1 minus 0. There's 0 minus ID3. So my supply current will look something like this. So now what did I do to my supply current? Polluted it, right? It's not a sine wave anymore. I've added harmonics. Remember, what was always our objective in all of these circuits? To find the equation for current, right? Because if I find my equation for current, I can calculate power factor, I can calculate THD, I can calculate power consumed, I can do whatever I want from the chapter 2 stuff, right? Now this is like our case where we used Fourier series before. Here I know what my voltage waveform is nice and defined. My current waveform is messed up. I don't know how to write an equation for current, so I will utilize Fourier series like we did before. So here we go to our, our cheat sheet of Fourier series for our full wave rectified voltage waveform. That will have, an average value of some sort, and then lots of harmonics. So this is the average value from the Fourier series. Again, you don't have to derive the Fourier series. The sheet is there for you, right? But this is the value of the average value of voltage, the DC value, and this is the nth harmonic for n is equal to 2, 4, blah, 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 for the full wave rectified sine wave. So this is the output voltage in the Fourier series. Now, how do you go about finding the current? Remember, we will find the current at every single harmonic. We take the voltage at each specific harmonic divided by the impedance at that specific harmonic. Which impedance are R plus j omega L. J omega NL. Right? N would be the number of the harmonic order there. And that's basically what they say in this slide. That's basically what we have here. And we said in the textbook there's a very good example that goes through. Did anybody solve it? The example we talked about last class? Come on, please. Go back and solve the example. Okay. How about if I increase the inductance? Remember we said if I increase the inductance, I can sort of assume that I can model this inductance as a current source. If I maintain this as a fixed current, what do you think these waveforms will look like?
I think it's follow the actual output voltage.
They will follow the output voltage?
Sorry.
This is a fixed current. Fixed current, DC. It's a fixed. So I output looks like what? I output looks like DC. This was I output. Now my I output looks like this. So now what will the diode currents look like? Exactly. Right? And how about my supply current? Square wave. Right? This is fictitious, of course. There's no such thing as, but sometimes in power electronics we always use this so that we can easily draw waveforms. I don't have to draw something, because let's say, I will answer your question, but let's say you're asked to, what is the approximate value of total harmonic distortion for a full wave rectifier with an RL load, right? As an engineer, this is easy to calculate because let's say the equation for total harmonic distortion is what? Is all your harmonics over your full RMS current, right? If so THD is a ratio between what? It's a percentage, it's a ratio between your harmonic squared, all your INs squared, divided by your full current squared, right? The sum of all your harmonics divided by the sum of your current squared. If they are the same, if there is no harmonic, if you have a sine wave, then your current is a sine wave in the bottom. It has an RMS value equal to V max over I max over square root of 2, and it's harmonic. There's no harmonic. There's only the fundamental, which means here I'm only looking at the harmonics, so the harmonics will be 0. 0 over your I, take the square, is 0. So the THD in that case is 0. Here, square waves and stuff like that is easy to find the RMS value for a square wave. What's the RMS value for a square wave of peak value I?
I squared 3. There was another one.
Think before you answer. Well, that was a square wave that was square. This is a square wave with no average value. That one was a square wave with average value. It was a PWM wave. But here, yeah, again, you have a square wave. What is RMS? RMS is square mean under the root, right? If you square this, what do I get? I get this. I get this, right? I get this. I get this. What do you get? Just the DC value, right? So, and then, okay, take the mean value of that and put that under the root. What do you get? What's the average value of a DC value? The DC value. What's the square root of a DC value squared? It's the DC value, right? So what is the RMS? What is the, what were you saying? RMS value of, yeah, what's the RMS value of this waveform? I. Right? And then from your Fourier series sheet, you have the RMS the Fourier series expansion for your square wave waveform. So you can look at that. It will have third, fifth, seventh harmonic. You take those, put them here in terms of the I, and divide it by the I. You can easily calculate it, what I'm saying. But for example, something like this waveform here, how do you calculate THD? Current THD. It's very difficult. Because then you have to calculate, look at the voltage waveform, do the Fourier series for the voltage waveform, calculate the impedance at every frequency, divide them by each other, calculate the current harmonics, and then do THD. Right? Versus if you want the back of the envelope type thing, okay, make it a square wave. I can easily calculate current THD that way. Right? Because it's easy. Yes? Make the inductor infinite. Which is, again, fictitious, but it's you can easily use it to play around with the numbers. Yeah. Okay, so that's what we were just discussing. And this is the RMS of that waveform. Any questions? Fine. Okay, then they go through some simulations. You should do that in the lab. And then this is the case with a RL and a source. So this is a little more complicated, but it's still should be hopefully straightforward. So now what do we have? We have RL and a source. Okay. We started with inductor current equal to 0. So what's happening here? So my source, let's say my source looks like this. This is my input voltage. Right? This is a full wave rectified waveform. Right? We agree? It's a full wave rectified waveform? So, since this is, so here I will see a full wave rectified waveform. Here. If the voltage on this side is less than the voltage on this side, is current going to flow? Remember, current flows from the higher voltage side to the lower voltage side. So, if the rectified waveform has a higher value than my DC source, then current will flow. And that's why in the previous case, without the DC source, current was started to flow all the way when time was equal to 0, as soon as we applied voltage. Right? But how about here? Here I have a DC source. Right? If this DC source level is here, what happens? Initially only there's a discrepancy, but after that there's no discrepancy.
Mhm. That's very important.
Initially, can current start flowing? Yeah, initially this is my DC value and this is my AC waveform.
It has to line up above the DC value.
Yeah, when the AC waveform is higher than the DC waveform, right? So at some point here, very close. That's why the discrepancy is only in the transient. We don't care about transient, but they included the drawing here, so I wanted to explain it here. So that's why if you erase this junk here, you will see that. See, there's a period here where current is not flowing. If current is not flowing in this circuit, what does the output voltage look like? The output voltage is the voltage across the R, L, and the source together. What does the output voltage look like if the current is not flowing in this circuit?
CDC.
What is the output voltage? Huh? The voltage across R, L, and source. What is that equal to if there's no current flowing? Come on. What is the voltage across R, L, and source if there is no current flowing in this circuit? Huh? It's the DC voltage. It's the DC source voltage, right? And that's what we have here. Initially, the output is this DC value, right? And then, as soon as the the full wave rectified waveform is greater than the DC value, then diode 1 and 2 conduct, right? And current starts flowing again, and I'm happy, right? And the circuit is nothing but what? This source here, then R, L, and my equivalent source here. Yes?
Sir, can the load feed power back to the source?
Yes. We see that's a PV panel. I can remove this and put a PV panel, right? We will do that later, actually, in this chapter. Yeah. So it will be the first grid-connected converter that you come up with. Yeah. But we will do that later. Yeah. Not here, not in this case. Why not in this case? But here we're not doing that, right? Am I doing that? Here I'm actually taking power from my source and charging my battery. Remember the passive sign convention, this is a source with current coming into the positive terminal and out of the negative. So here I'm charging this battery.
But when the source is AC,
This is an AC source.
yeah, so when the source is AC, and at certain points the source is null, it's at 0. Can,
Here you mean?
yeah,
Okay, what's your question?
so can the VD go through, the power coming from VD go through the diodes and into the source?
Okay. Let's agree on something, right? If that's passive sign convention, you agree with passive sign convention? If this is my source and current is coming into it, I'm charging it. If this is my source and current is coming out of it,
This way.
I'm discharging, right? In this case, can I do this? Current will come out here, which it means it will have to go through here, opposing this diode polarity. So I cannot do that. You cannot do that here. Right? So we will see later when we make these SCRs, when we make these thyristors, and we have an RL and a source case, we can make the voltage negative. We can make this output voltage negative, but we will maintain the same current polarity. So it's like, so yeah, I will make the voltage negative. So I will, this here, I have output voltage. Remember, what is my average output here? Is it positive or negative? My average output, the average value of this full wave rectified waveform is a positive value. When we add SCRs, we can make that value negative if I have an inductive load. And then if you make it negative and you keep the polarity of the current the same, then you flip the polarity of the voltage. So now I have, instead of, current is still going in here. Initially it looked like this, but now I would flip the polarity of the voltage. I will find a way to do this. Then in this case, I'm putting current into the negative and coming out of the positive. This means this source is now feeding this battery is now feeding my AC source. We will do that later in this chapter. So it will be an example of a grid-connected converter. But before we get that, we have a few minutes left. So this is initially what's happening, right? There's no current flowing. But then what happens after that?
Then write it over the DC value, and once the source value is greater than DC value.
Then in the case of inductors, in case of having, because you have an inductor, current does not. Again, let's talk about the resistive case. In the resistive case, what would have happened? Current in the resistor would have started rising here, and would have stopped here. This is the resistive case. Do we agree? If I have a DC source of this value here, and a resistive load, this would be the output current. Right? Now we have an inductive circuit case. In the inductive circuit case, what happens? Current starts rising in the same place, but the shape of the current is a bit distorted. Right? It will be delayed. The peak will be delayed with respect to the resistive case. And then it tries to start falling down. It will fall down after the resistive case. It can fall down, here in the middle, if you've chosen the inductor value as such, but it won't happen. That would have happened only in the half-wave rectifier. In the full-wave rectifier, what's really happening? As soon as the current starts falling down, what is going on? The voltage, again, what is the inductor voltage? Voltage is Vs minus Vr. Same thing, Vs minus Vr minus VDC. Right, so you find you have a different additional player here. So if you increase the DC voltage, what will that do? Or if you decrease the DC voltage, what will that do? Make the DC voltage zero. If you make the DC voltage zero, inductor current will never fall down. Will never fall. It will always be continuous. Right? If you increase the DC voltage, what will that do?
Will it take longer for the voltage across the inductor to rise high enough? Won't it take longer for the voltage across the inductor to get the higher positive value? So then the current won't it fall more?
It will fall quicker. The current will fall quicker if you increase the value of the DC voltage. Right here. Look, what does the circuit look like? My AC source, and then my resistor, my inductor, and my DC. Oops, sorry. AC source, resistor, inductor, DC. Here, 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 here. V, AC, VR, VL, VDC. So, VAC equal to VR plus VL plus VDC. VL is equal to V source minus VR minus VDC, right? So, let's assume VR is 0. Let's assume VR is 0. Right? I have Vs minus VDC. If VDC increases, then it makes what? It's like if the supply voltage is falling down, and I put my VDC up here, right? Then at some point, VDC and Vs are equal. VL is equal to 0, and I expect my inductor current slope to equal 0. Right? Inductor current slope will equal 0 if these are equal to 0. Right? If I bring this up, if I bring the DC source up, what's going to happen? I push it to the left. I push it to the left. If it pushes this to the left, it means what? Current will fall, or the current will have a slope of 0 before. So the potential of it falling, so the idea of trying to tune it to fall, in this gap between the resistive case can happen if you keep increasing the value of the DC source. Right? So increasing the value of the DC source will do what? Will make this current, will push this current to the left, and the point at which the current slope becomes 0 will be moved to the left. At some point, you can bring the current down to 0. So this circuit can be operating in continuous mode like this if I have a small value for DC and a significant hefty inductance. Right? Now I keep everything the same, but increase the value of the DC source. If you increase the value of the DC source, what will that do? We said it will bring my inductor, the intersection at which the voltage across the inductor is equal to 0, to the left. So it means the current will stop rising at that point, stop falling at that point. So the current will fall. The current fall will move to the left. The peak value will move to the left. Everything will move to the left. Inductor current, the whole thing will move to the left. So at some point, you move it enough to the left such that it intersects with 0. We'll stop here. We'll do this again next time, and then we'll wrap up. Do the rest of this. Anyway, please do the exercise on the